Take the number 4. In how many ways can you write it as a sum of whole numbers if order doesn't matter? 4 by itself. 3 and 1. 2 and 2. 2, 1, 1. For 4 ones. 5 ways. No more, no less. That count has a name. P of n. The partition function. So P of 4 equals 5. Note the partitions of 1, 2, 3, and on. And you get this innocent-looking sequence. But it doesn't stay innocent. By 100, the count is already 190 million. By 200, nearly 4 trillion. And yet, this wild count of nothing but whole numbers is captured, astonishingly well, by a single smooth formula. Look closely at it. There's a square root, there's the number e, and right there, deciding how fast it all grows, is pi. In 1918, Hardy-Ramanujan found that formula, and the way they found it is one of the most beautiful arguments in all of mathematics. So here is our question for the whole film. The partitions of a number are pure counting. No circles, no geometry anywhere. So why on earth should pi decide how fast that count grows? Start with something you already trust. 1 over 1 minus q is just the geometric series. 1 plus q squared forever. Now swap q for q to the k. This factor's powers are bookkeeping. The term you pick says how many parts of psi you use. None. 1. 2. 3 of them. So multiply one such factor for every possible part size. 1, 2, 3, and on forever. Call that infinite product big F of q. And here is Euler's miracle. Expand that product, collect powers of q, and the coefficient sitting in front of q to the mean, exactly p of n. The number of partitions. But wait, why should multiplying these factors count anything at all? Take a moment. Here's the answer. To build a q to the 4, you pick one power from each factor so the exponents add up to 4. Every such choice is a partition of 4, and there are exactly 5 of them. The product doesn't approximate the count. It is the count. So the whole problem just moved. Counting partitions is now reading a coefficient off one infinite product. We need just one number out of that whole product. The coefficient of q to the n. To get it, we go into the complex plane, and let q be a point on a circle around 0. Pick a circle of radius a little under 1. That's our contour. And walk cow all the way around it. Now the trick. Go around a circle and every power of q averages out to nothing. Except 1. Divide by q to the n plus 1 first, and only the nth power survives the trip. The integral is a tuner. It keeps the term you want and erases all the rest. Point that tuner at our generating function, and we get an exact expression for p of n. No more guessing, just one contour integral of big F around the circle. But here's the catch that sets up everything. Big F is small and tame near the middle, and it does all its interesting growing out at the rim, where q approaches 1. To feel that, we have to push the contour outward, right up against the edge. And the rim, it turns out, is a dangerous place. Remember, F is a product of factors 1 over 1 minus q to the k. Each one explodes wherever its denominator hits 0. That is, wherever q is a root of unity. And those roots of unity are everywhere on the rim, and denser, until they leave no gaps at all. The unit circle is a solid wall of singularities, a natural boundary. There is simply no reaching across it. But not all of them are equals. The biggest, fiercest one, the factor that dominates everything, sits right at q equals 1. So let's zoom in on q equals 1. Slide q in from the inside along the real axis, write it as e to the minus t, and let t shrink towards 0. Watch both sides at once. As q creeps up to the wall, the value of f doesn't just grow. It erupts, racing off to infinity. Why does it erupt? And how fast? Here is the calculation Hardy and Ramanujan leaned on. Take the log of f. The product becomes a sum of logs. Expand each log as its own little series, and after you regroup, every term has this shape. When t is tiny, e to the mt minus 1 is almost just m times t. Make that swap and the whole thing collapses into 1 over t, times the sum of 1 over m squared. And that famous sum, Euler's basal sum, equals pi squared over 6. There it is, the very first pi, sneaking in through a sum of reciprocal squares. This isn't a lucky accident. It's a deep symmetry called the modular transformation. It trades the wild behavior at q equals 1 for the tame behavior at q equals 0, where the product is easy. So, a question. The room is crowded with singularities. Which one actually controls the growth of p of n? One at q equals 1, the root with the smallest denominator. Its blow-up is the strongest by far. The others matter too, but they're whispers next to it. We'll come back for them. The takeaway, right next to the wall, f grows like e to the pi squared over 6t. Now hold on. Let's play devil's advocate. We have a formula for p of n. So we just plug in n and we're done, right? Not so fast. Look at that little squiggle. It does not say equals. It says asymptotic to. The two sides only get close, in a relative sense, as n runs off to infinity. And the gap is real. The gap is real. The gap is real. At n equals 100, the true count is 199 million. About 5% too big. Close, but not the answer. Why too big? Because we only listen to the loudest singularity at q equals 1. But we can't even cross that wall. It's a natural boundary. And a real proof has to ride along it, account for every other root of unity, and bound the leftover stretches. The saddle alone is a sketch, not the proof. So let's amend what we said at the start. Yes, partitions live in the coefficients of that product, but to read them out exactly, every root of unity has to get a vote, not just the one at q equals 1. Hold that thought. It's the whole idea of the circle method. Here's the engine. Inside the integral, big F blows up like e to the pi squared over 6t. But pulling out q to the minus n adds an e to the nt. Multiply them, and the size of the integrand is e to the power of 1 function. Call it big phi. And big phi is a tug of war. The first term, with its pi, screams make t small. The second, carrying n, screams make t large. Two terms opposite ways. Draw them. The pi term falls away like this. The n term rises like this. Add them, and you get a valley. A single graceful valley with one lowest point. So, where does that valley bottom out? The whole answer hides at that one point. Right here, at the bottom. Mathematicians call it the saddle point, the spot the whole integral is ruled by. To find it, set the slope of big phi to 0. Solve, and the saddle sits at t star equals pi over root 6n. As n grows, the saddle slides toward 0. Toward the wall. Exactly as we hoped. Now, put the saddle back into big phi. The two terms turn out exactly equal there. And they add up to this. Pi times the square root of 2n over 3. There it is. The exponent in the formula, with pi standing right in front. And the bump out front? That comes from how wide the valley is. Approximate the integral by a Gaussian around the saddle, with the extra square root factor the modular transformation hands us, and the width delivers the 1 over 4n root 3. Every piece accounted for. The takeaway: one saddle point turns a hard integral into that clean exponent. Pi and all. Back to the rim, one last time. The leading term only listened to q equals 1. The circle method listens to all of them. Slice the circle into little arcs, one around each root of unity, and add up what every arc contributes. And here's why it works so beautifully. Each root contributes a term, but the root with denominator k carries the exponent divided by k. So q equals 1 dominates, q equals -1 is echo, and the rest fade fast. A few terms is all you need. Hardy and Ramanujan tested it on a giant. For n equals 200, McMahon had counted the partitions by hand. Nearly 4 trillion. Their series with just 8 terms gave 3.97 trillion, and then this, a number ending in 0.004. Round it to the nearest whole number, and you land exactly to the digit on McMahon's count. A formula from contour integrals and saddle points, nailing a combinatorial answer dead on. Which brings us back to the question we started with. Why should pi, born of circles, rule a count of whole numbers? And now, we can answer it. The moment we turned counting into an integral around a circle, geometry walked in the door. Pi was waiting in the width of the saddle, in the Gaussian that the modular symmetry handed us. The circle was there all along. So, here's the whole story, in plain words. To count the ways a number breaks into a sum, we packed every partition into a single function. Then we turned that count into a walk around a circle, and found the answer is ruled by one special point, where, almost like magic, pi appears. And the road we took spells the name of the method itself, the circle method, CIRCLE. Count the partitions. Infinite product. Recover one coefficient with a contour. A whole crowd of singularities on the rim. Lift the behavior near q equals 1. And extremize the saddle point that hands us pi. One last thought to carry with you. Our series only got close, then rounded. But years later, Rademacher found a way to make it exact. A convergent series that gives p of n on the nose. How?